At the beginning of this section, we should ask ourselves the following question. Do we need to control a system at all? Actually, we need to control a piece of equipment when a disturbance exists, the disturbance is not tolerable, and when the system is not self-controlled. These requirements force us to put control on most equipment. The first feature is almost always present, since we live in a world full of changes. A disturbance is almost always not tolerable, except for in the case of a few process elements. For example, level disturbance could be tolerable for big tank, but possibly not for small vessels. Process items are almost always non-self-regulated. To control each piece of equipment, a control loop or control loops need to be installed to satisfy two requirements. The first one, placing the control loop on the parameter which is the main purpose of the equipment. The second one is placing the control loop on other parameters or other streams parameters to bring the equipment into its operating window. Now, the result of addressing these requirements could be the requirement to install 1, 2, 3, or more control loops around the equipment. For the first requirement, placing the control loop on the parameter which is the main purpose of the equipment, this is self-explanatory. If you have a heat exchanger on your PNID, you will find a temperature control loop on the pipe of the target stream as seen here. If you're dealing with a centrifugal pump, you will find a flow control loop. And if you have a compressor, you will find a pressure control loop, although sometimes you will find flow control. These two are interrelated. With a distillation column or a reactor, the whole purpose of the equipment is to change composition. So, on your PNID, it is likely that you will find composition control loops, as highlighted here. Of course, all of these control loops will be discussed in detail further ahead. Now, a control loop based on this requirement brings a piece of equipment onto its intended operating point within its operating window. Recognizing the main process purpose parameter is not difficult. Take a look at the following table. It lists the most common piece of equipment and their main process parameter that needs to be controlled. For tanks and vessels, the parameter to be controlled would be level. For gas vessels, it would be pressure. For moving equipment or rotating equipments like pumps, compressors, fans, or blowers, the parameter to be controlled is the flow rate or the discharge pressure. Sometimes it is both. And finally, for heat transfer equipment like heat exchangers, furnaces, and boilers, the parameter to be controlled is the temperature of the target stream. We'll see this in details further ahead. Now, for the second requirement, placing the control loop on other parameters or other streams parameters to bring the equipment into its operating window, we generally don't install a control loop for every single parameter to make sure that the unit operates within its operating window. We only install control on the weak point of the equipment, if the risk of reaching that weak point is high. Here, weak point means a process parameter related to the equipment, whereby if a process stream reaches that point, there is a chance of a process upset or of losing the equipment due to equipment failure. If the risk of such a condition is low, you may decide not to install any control loop for this purpose. If the risk of such a condition is very high, you may decide to leave this duty to the SIS, or Safety Instrumented System, rather than to the BPCS, or Basic Process Control System. and so not install any control loop for this purpose. SIS and BPCS will be explained in details further ahead. Now, the thing about risk is that it is a multiplication of probability and severity of consequence. For example, we need to decide if a pump needs a control loop or not based on the weak point concept. In general, pump manufacturers give a warning of damage to the pump if the flow rate drops below a certain level. Now, let's check the risk of this event for the three different following cases that you will certainly come across when reading your P&IDs. The first case is related to a pump in a closed loop. The second one is related to a small pump on a pipe. And the third case is related to a large pump on a pipe. Now, the probability of flow change for each case is seen here. For the first case, the probability of flow change or flow decrease is nil because it is closed loop with a constant flow. For the second and third cases, the probability of flow change is high, since the pump is on an open pipe. The severity of consequence for each case is seen here. In the first case, the severity of consequence is only the loss of the pump. In the second case, it is the loss of the pump, but the pump is small and inexpensive, so the severity is almost negligible. In the last case, the severity of the consequence is the loss of large expensive pump. And here you can see the risk related to each case. In case number 1, the risk is 0. In case number 2, it is almost 0. And finally, in case number 3, it is not negligible because you will lose a large expensive pump. And therefore, based on the probability of flow change and the severity of consequence, we can deduce the actions for each case. In the first case, no control loop is needed to protect the pump against low flow. In the second case, no control loop to protect the pump against low flow because even though there is a high change of probability flow change, the severity of consequence is almost negligible. But in the third case, you will need a control loop to protect your pump against low flow because there is a high possibility or a high probability of flow change coupled with a high severity of consequence because the risk here is that you will lose a large pump and an expensive pump. So therefore, you need to mitigate this case by installing a control loop to protect this pump. So from the three examples that you can see here, you can deduce that the statement that all pumps need to be protected from minimum flow by a control loop is not set in stone. And for this reason, on your P&IDs, you will see that some pumps are equipped with a control loop to protect them against flow change, while others are not equipped with a control loop. So from your P&ID, you can actually guess and identify the pumps that are critical to your process. Now, the methodology that we used here to decide whether or not we need a control loop was done for flow. Of course, this methodology can be reiterated for other process parameters, such as level, temperature, pressure, or composition. Take a look at the following table. It shows you the parameters that may need to be controlled as part of operating window. However, it should be stressed here that there is a large amount of room for judgment by the P&ID designer. For this reason, it is important that you check out the non-graphic zone of your P&ID and examine the notes and legend that the P&ID developer or designer felt it was necessary to mention. In this way, you will find, if applicable, the reasons behind the presence or not of a specific control loop. Now, the rest of this section will provide an advanced overview of the general control loops around the most common process elements. We will cover control loops for pipes, fluid movers like pumps and compressors, heat transfer equipment like heat exchangers and furnaces. Now, you may be surprised to see pipe control in this section, since a pipe is not a piece of equipment. Even though this is the case, the different control procedures for pipes are very popular in process industries, and you cannot find a single P&ID without a pipe control loop. For this reason, you must learn how pipe control loops are represented on your P&IDs. There are two main classes of fluid movers: liquid movers, such as centrifugal pumps, and gas movers, such as compressors. The common control component for all fluid movers is capacity control. Capacity control means controlling the flow rate generated by the fluid mover. Fluid movers may have more control components in addition to capacity control. In this video, we'll start by discussing P&ID control for centrifugal pumps. Then, in later videos, we'll discuss for other fluid movers, such as positive displacement pumps and compressors. Now, when talking about centrifugal pumps, we need to deal with two different but separate and independent control systems. And these are capacity control and minimum flow control. For capacity control, recall that the main function of pumps is to generate flow, so flow or capacity needs to be controlled. There are mainly two types of devices that can be used to adjust the flow rate of a centrifugal pump: control valves and variable speed drives, or VSD. Take a look at the following P&ID example. It shows the options we have for the control of a centrifugal pump. Option A shows capacity control using a control valve on a flow loop. This option is also called discharge throttling. Here, a control valve is installed on the discharge line of the pump. Option B shows control using a signal from the flow controller to the variable speed drive. Here, the variable speed drive, or VSD, is installed on the electromotor of the pump. This option controls the flow by adjusting the rotation speed of the pump shaft. So, to sum up, in option A, we basically adjust the flow of the pump by using a control valve on the discharge piping of the pump. And in option B, we adjust the flow rate of the pump by adjusting the rotation speed of the shaft. These are two completely different methods of pump control. By using a VSD, we are changing the location of the pump curve, while by using the control valve, we are changing the system curve. Now, the functioning of centrifugal pumps is beyond the scope of this course, but if you feel like you want to know more, then please check out our bestseller course on centrifugal pumps, principles, operation, and design. And don't forget to ask us for coupon codes. Finally, to finish off this video, keep in mind whenever there is more than one control method for controlling a piece of equipment, both of them can be implemented through a split range control loop, as we have seen in a previous video. For example, the capacity of a centrifugal pump can be controlled by a split range between a variable speed drive and a control valve on the discharge of the pump. We will see a P&ID example of this in the practice session. Okay, so now we know that there are at least two methods of controlling centrifugal pumps, by control valve and by VFD, or variable frequency drive or variable speed drive. Now, the question is, which one should be used? Sometimes, when we are not sure, we use both of them in the form of split range control. If we cannot afford to use both of them in the form of split control, we need to choose one of them. Traditionally, we use a control valve because it is an older technology and a cheaper technology. However, there are cases where a VFD works better. This is the reason why you will find control on centrifugal pumps either by control valves or variable speed drives on your PNIDs. Now recall, a control valve is generally installed in the discharge line of the pump, and the VSD or VFD is installed on the electromotor of the pump. These two methods of adjusting the flow rate of a centrifugal pump are named final control elements. Take a look at the following table. It summarizes some process reasons for using a control valve or a VFD. Now, since control valves generate more shear on the fluid, they are not good for shear-sensitive liquids like oily waters or biomaterial. However, the advantage is that control valves work for all types of piping circuits. On the other hand, a variable frequency drive generates less shear on the fluid, but it doesn't work in systems where the majority of the pump head is used to overcome static pressure rather than pipe pressure loss. So now, based on this table, you understand the reason behind a centrifugal pump control based on a control valve or a VFD once you come across it in your PNIDs. The concept of minimum flow control is shown in the following PNID example. Let's assume that this pump has a capacity of 200 cubic meter per hour. The vendor specified that the minimum flow rate of the pump is 100 cubic meter per hour. We can provide a recirculation line from the outlet of the pump back into the inlet line. If the flow rate into the pump is 165 cubic meter per hour, the pump is happy, since its flow is higher than the minimum flow. In this case, the sensor on the pump outlet sends a signal to the control valve on the recirculation line and it remains closed. However, if the flow drops below 100 cubic meter per hour, for example 80 cubic meter per hour, the flow sensor on the outlet will send a signal to the controller to say, "Hey, I'm short of my minimum required flow by 20 cubic meter per hour, and I'm worried about the pump. Please open the valve enough to recirculate 20 cubic meter per hour, so we can fool the pump into thinking that the flow is 100 cubic meter per hour and make it happy." So the control valve on the recirculation line will be partially opened to provide a flow of 20 cubic meter per hour. And this flow is sent back to the inlet to satisfy the minimum flow condition of 100 cubic meter per hour and prevent damage to the pump. This is the concept of minimum flow control. Now, it is important to recognize here that this trick only increases the flow rate inside the recirculation loop to a number higher than 100 cubic meter per hour to fool the pump. We are not able to increase the overall flow in the whole upstream and downstream piping system. The flow in those pipes is still 80 cubic meter per hour. The point here is that the sensor should be placed as close as possible to the pump and within the recirculation loop. Now, the question is whether we need a minimum flow control loop for all centrifugal pumps or not. The answer is no. You will not see this type of control on each centrifugal pump on your PNIDs. We don't need minimum flow control loop for all centrifugal pumps. The following examples of pumps may not need a minimum flow control loop. For example, small pumps of less than 5 horsepower. They need it, but they are inexpensive, so we don't bother to put an expensive minimum flow control loop on them. Another example is pumps in a circulating closed system. They may not need a minimum flow control loop because the flow in such pumps is fairly constant. However, the following examples of pumps may require minimum flow control. For example, large pumps of 5 horsepower or more, and pumps on the mainstream. The rule of thumb for providing minimum flow control is as follows. For pumps with power lower than 5 horsepower, no minimum flow line is required, as mentioned before. When the power of the pump is between 5 horsepower and 10 to 20 horsepower, you need a continuous minimum flow line. As seen in this PNID example, instead of going to the expense of installing a control valve, we can put a restriction orifice on this line. By doing this, we are always recirculating a portion of flow, even in cases where flow to the pump is higher than the minimum flow, and we don't really need recirculation. So we are continuously wasting energy, and we know that, but the pump is so small that installing an expensive control loop for them is hard to justify. For pumps with power between 10 to 30 horsepower, you need on-off minimum flow line. This is a cheaper option than installing a control valve. In this case, the flow control loop will just provide an on-off function. Finally, for pumps with power higher than 35 horsepower, you need a minimum flow line with a control valve. This is the most complicated, most expensive option, but it is the most common method of controlling minimum flow in centrifugal pumps that you will see on your PNIDs. This type of control can be done with at least 2 different arrangements, with a flow loop, as seen here, or with a pressure loop. We have the option of controlling by flow sensor or by pressure sensor. Usually, we go with the flow loop. Now, when there are 2 or more pumps in parallel, as highlighted here, and only one of them is operating and the rest are spares, a minimum spill back pipe from the common header works well. The question is what the minimum flow should be when there are parallel operating pumps. We have 3 options for providing minimum flow lines for parallel operating pumps, and that you will probably see in your PNIDs. In option 1, a shared minimum recirculation pipe is provided for 2 operating pumps, as highlighted here. In option 2, dedicated recirculation pipes are provided at the beginning, but they are merged in downstream before getting to the upstream reservoir. In option 3, fully dedicated minimum flow pipes are provided for each pump in parallel arrangement, and both are operating. Now, the problem with option 1 is that the flow from the 2 pumps compensate for each other, and the sensor cannot tell if one pump is starving or not. So the sensor could be telling you that the system is okay, but one of the pumps could actually be in bad shape, Option 3 may be the best system, but it is the most expensive option. For this reason, most companies go with option 2. And that is why it is most likely that this arrangement is on your P&IDs. But in any of the cases, at least 2 different types of control system can be applied on the minimum flow pipe as shown in this next figure. In the left-hand P&ID schematic, the total flow is used for the purpose of control, while in the right-hand P&ID schematic, the minimum flow is used. The issue with the left-hand P&ID schematic is that the control system cannot recognize which pump is suffering from the flow lower than the minimum flow. And the issue with the right-hand schematic is that the control system cannot provide the flow to satisfy both suffering pumps if both pumps are suffering from flow lower than the minimum flow, but with uneven difference to the minimum flow. Because more than 80% of pumps used in the process industry are centrifugal pumps, many people are not familiar with how to control positive displacement pumps. You cannot use the same arrangement for controlling a positive displacement pump as for a centrifugal pump. It will not work. If you put a flow loop on the discharge of a positive displacement pump, it won't change the flow at all. There are actually 2 main groups of positive displacement pumps: reciprocating and rotary. Each has its own symbol, and this was covered in detail in a previous video. In this video, we have invented our own symbol, shown here with our initials, WR, to cover the whole range of positive displacement pumps in this section. Of course, this is not a symbol that you will encounter or use on a P&ID because it is not recognized. Now, positive displacement pumps are not sensitive to minimum flow, so all we have to worry about is capacity control. For capacity control, again, we have 2 options: by recirculation pipe and by variable speed drive. These options are different from the options for centrifugal pumps. We'll see this in details in the next couple of videos. To understand the way we can control the capacity of a positive displacement pump, you need to picture the positive displacement pump as a stubborn mule, so you cannot convince it to decrease its capacity. The only thing you can do is that you divert a portion of its capacity out of the main discharge pipe. There are at least 2 arrangements for capacity control of positive displacement pumps using a recirculation pipe. The first arrangement is shown in this P&ID schematic. This arrangement shows how we can control the capacity of the positive displacement pump by using a recirculation line. The flow sensor is located on the discharge line outside of the recirculation loop. If the rating of the pump is 10 cubic meter per hour and the equipment downstream is only drawing 8 cubic meter per hour, this means we need to recirculate 2 cubic meters per hour. Even though this arrangement is similar to a minimum flow configuration as for centrifugal pumps, the design basis for the recirculation pipe is different from a minimum flow protection pipe. Also, note here that the flow sensor is located outside of the recirculation loop. The arrangement shown in the next P&ID example is somewhat complicated and not popular for that reason. Here you can see a control valve on the discharge of the positive displacement pump, and you may be surprised that it doesn't work. In fact, you are right. Controlling the capacity of a positive displacement pump with discharge throttling doesn't work. But here we have added a recirculation pipe to make it workable. The control loop on the discharge of the positive displacement pump could be a level loop or a flow loop, depending on the situation. The control loop on the recirculation pipe should be a back pressure control loop. We may, of course, choose to replace the back pressure control loop with a back pressure regulator. The second option for capacity control of a positive displacement pump is using a VSD or a VFD as depicted in this PNID schematic. Here we know that the positive displacement pump is stubborn, but we overcome this by managing it from its root. We control the speed of the pump shaft. The capacity of the pump is controlled by a flow loop. A flow sensor on the discharge line sends a signal to the flow controller, which in turn sends a deviation signal to the VFD on the electromotor of the positive displacement pump. The VFD will, for example, decrease the speed or RPM of the motor, which will decrease the flow rate of the pump, or inversely increase the speed of the motor, which will increase the flow rate of the pump. The third type of positive displacement pump control is only for reciprocating pumps. An animated example is seen here. In the reciprocating type of positive displacement pumps, a piston or a membrane does a forward and backward movement repeatedly in order to achieve the pumping. The third method of controlling the capacity is applicable only to reciprocating pumps, adjusting the span of the member's reciprocating movement, or simply adjusting the stroke. Take a look at the following PNID schematic. The stroke adjustment can be done by attaching a servo motor to the stroke adjustment lever of the pump. Then the signal from the flow control loop can increase or decrease the stroke length, which will adjust the flow rate of the pump.